So back to class. For schedule, if you missed it, there was a really interesting recitation about sustainability projects. Very compelling. No recitation in the next week. And we're going to start an electronic sequence now. So you've laser cut smaller things, you've machined bigger things, you've 3D printed. This week, we're going to go how you make circuit boards, and then we're going to do inputs, outputs, and networking. And with all of that, you'll be ready to build machines. So this week is making a circuit board, attaching the components. To look ahead, the group assignment would be to characterize the processes in your lab and to send a design to a board house. The individual one is make and test an embedded microcontroller system you designed. So we want you to not just make it, test it. It has to have a processor. Extra credit is use more than one process. And so to illustrate, Quentin did a nice job on this when he did Fab Academy. Just, it well documented all the steps of making the circuit board, and then attaching the components and programming it. As well as some experiments. Then what's amusing is when Isaac had to do this assignment, he wrote the prayer to Quentin because Quentin was his instructor. So, Almighty Quentin, guardian of circuits, ruler of solder joints, we call upon your infinite wisdom to guide our shaky hands and steady our connections. When the components fail to align and the boards refuse to blink, we look to you, O Quentin, for salvation. Bestow upon us your grace and the power to debug. Let not our resistors smoke, nor our traces burn. In your name, we align our masks, we fix our solder bridges, and may the electrons bend to our will. Amen. And while that was a nice recognition of what Quentin's help, many of the elements in this prayer you will run into and understand the need for the prayer. And then maybe my favorite assignment was somebody who combined this with make something big. And so he made a circuit board that works that was about 7 feet tall or 6 feet tall. So he machined a giant circuit board, and in these huge components, he put the real little components, and this is actually a working circuit board. Okay, so that's what we're going to do this week. So to make a circuit board, there's a number of techniques. There's a thing called dead bug. And I don't recommend you ever do this, but I'll mention it. Dead bug is because it's sort of, the leads look like a bug, dead bug on its back. There's no circuit board, there's no anything. You just take all the components and you put wires to them. Terrible, messy thing. Occasionally it's done at very high frequencies, for example. I just mention it because you might encounter the term dead bug. Commercially, this is most done by etching. Most of the circuit boards you see. One thing that's non-trivial about etching is before you can make it, you need to transfer the image. What's good about etching is you can make very tiny features, and it's the same time to make a whole batch as one of them. So this is a page that describes the steps of how your image gets on the board using lithography. You can do toner transfer as a way to make etch masks. You can print, and this is a description of that. Um, but here's the issue. The most common etchants are very hazardous. So SDS are material safety data sheets. And if you read the SDS for the etchants, you'll find they're very hazardous chemicals. There's a real disservice done when they're sold to hobbyists, because if you pour these chemicals down,
Neil, Neil, we lost you. Your audio. Neil, Neil.
um,
Um,
okay, is the audio back now?
yes,
Yeah,
yes.
you're back.
Yeah,
Yeah, it's
occasionally it
good.
drops out. I don't know why. So if you pour the etchant down the sink, it etches your pipes. And then much worse than that, you're putting these very nasty chemicals in the environment. And so when we use these at MIT, there's a very professional waste removal service that has to stabilize it. Now, you can do a little bit better with kitchen chemistry. So this was a page on using citric acid and peroxides. But the first issue with etching is the very serious chemical waste. Another issue is the water consumption. See if this loads. And so if you make a square meter of circuit board, it consumes a cubic meter of water and turns that into chemical waste. And then this is an article on all of the waste coming from PCB fabrication. So it's convenient when you send it out to a board house that I'll talk about, but you need to be aware of all the waste generation. So for all of those reasons, it's most commonly done commercially, but you're not going to etch circuit boards. Instead, the standard process we use is machining them. And in a minute, I'll talk about lasers also. So this is slightly out of date only because these are videos that date back to the original Google Glasses. So this was a student who made nice videos. The workflow is a little bit out of date, but it shows the basic process. And here's the key. So to get to the punchline, this is the essence of it. Here's the circuit board in a little milling machine. Here's the, let's see, Marius is noting energy USB. Here's the cutting tool. And then here's the milling process. So what's great about this, one thing is there's no lithography. Just as soon as you have the design, you can send it out. And the other key thing is it's just making a little bit of dust. This dust, and I'll talk more about the materials, isn't at all hazardous. It's a little bit of dust to vacuum up. And every board you make can be different. There's no setup. The downside is the feature sizes aren't as small as etching, and it's not a batch process, but it's great for quick turn prototyping like we'll be doing. So you're going to etch. Now, you're going to machine. Now, some of the processes we do are variable. This is one that's completely consistent. So on the left, I'm showing when you machine the circuit board, it should come out looking like this. Every time the settings are the same, every time they're perfect. On the right, I'm showing, this was a student in the Fab Academy. This was their homework for this week. And I don't even know how you can do this. I'm not clear what went wrong. Yeah, I don't have an easy tip to explain this. This was just a bad bit and bad stock and a bad machine. All sorts of stuff have to come together to make such a mess. But don't remotely accept that this week. Um, everybody's boards this week should look like what's on the left. There should be no trouble making a perfect board. If it's anything other than what you see there, step back, check your tools, check your stock, check the condition of your machine. There should be no variability. So we're going to be using little tabletop milling machines. This is a link to the CBA tools, but just to illustrate, the Carvera is a nice milling machine that automatically changes the tools. That's about $5,000. Behind me is just one of these little Lunyes, and this is just a few $100s. I'm very happy with these, with one note, which is the for these little machines, and I'll add a note on this, is the spindle they ship with has too much run out. It's the tolerance. And so the run out is the difference between the tool diameter and the cut diameter because it's not perfectly aligned and vertical. And so on these little machines, I upgrade the spindle to a higher quality one that's still just a few $100s. So it's under $1,000 for one of these little machines with a better spindle. This one you have to manually change the tool, but other than that, the kind of boards I showed you, I make on this little one behind me. So you're going to use these little milling machines that are surprisingly high resolution. And then you're going to use end mills. This is a standard one. This is like what you used for large format machining, but it's a tiny one. So this one is 1/64th of an inch, 15 thousandths of an inch. That's a standard size we use for making circuit boards. That one is about $24, and it could make roughly 24 circuit boards. So you use about $1 of the end mill life, unless you break the end mill, which I'll talk about. There are smaller end mills you can use to make even tinier features. There are bigger end mills we use to cut out the boards. And then there's two other options. So these, the end mill I showed you it's a straight end mill, makes very clean traces. But if you're not careful, and I'll describe careful, you can break them. These V-bits have gotten better. So instead of flutes, it's just a sharp corner. It is coated, and it spins around. So these are noisier than the real end mill because it's not a flute cutting. And they vibrate more because it's sort of whacking at it. But the machine is stiff enough, and these are sharp enough that you can make really nice boards with these. And the V-bits, it's roughly impossible to break them, and they're only $1 each. And there's also both a feature and a bug, which is, and Adrian, I'll come to that next. The feature and the bug is because of the V shape, the width of the cut is proportional to the depth of the cut. So with a V-bit, you can actually vary the trace size intentionally, but if your board isn't flat, you'll actually get a varying size over it. So, but these are good as kind of a workhorse in your lab. And then finally, there's a nice compromise, which are these tapered bits. So these conical tapered bits are much more robust than the straight bits. It's harder to break them, and they have the flexibility of the tapered bits. So if you're careful, the straight bits work great, but beginners can easily break them. That's not hazardous because they're so tiny. It's just hazardous to the budget of your lab. The V bits are surprisingly, once you get used to, they're a bit noisier and vibrate more. Once you get used to them, they make really nice boards. And then the taper bits are a really good compromise. Now it's key you know the dimension because a key parameter is going to be, so if we have copper, we have the mill, we're making a trace, and this, a key thing for this week is what's the actual spacing, which is how close can you be together, and then how skinny can you make a trace and have the trace still survive, and I'll talk about that. You have a end mill, you have the material, and I'll talk about that in a minute. Next is the fixturing. You need to hold it in place. One way you can do that is with tape on underneath. Another way is with clamps. The issue with clamps are when you clamp the board, it's very important that it doesn't bow, that there's no bending of it, because if you bow the board, there's stress concentration and this can break end mills. So you can clamp if you have really nice clamps that spread out the clamping force, or you can use tape underneath, but you want to make sure the board lays flat. Then a key thing is the underlay. So here's the board that has the copper on it that you'll be machining with your end mill. Then underneath this is an underlay, and then this is on the bed of the machine. So this is the machine bed moving. This is a sacrificial layer. So when we cut out the board, we're going to cut all the way through, and you cut into the underlay. If the underlay isn't flat, you'll have a problem because we're only making a tiny cut. If the underlay isn't flat, your board won't be uniform. And over time, you're cutting into the underlay. And so after you make a number of boards, if you look at the underlay, there's a lot of outlines cut into it. And eventually, when there's enough cut into it, the underlay doesn't hold the board very well anymore. So the underlay is an important consumable. And one of the things that can go wrong is you leave it there too long. You periodically need to replace the underlay. Okay, so then you have your end mill that's going to be cutting. It goes into a collet, that goes into a spindle. The spindle goes onto a gantry. The gantry goes to a moving system. You have the underlay, the board, and the copper. And this distance, you want to get good to less than a millimeter. This is a very tight tolerance, but we'll talk more about this in machine building. This is what's called a force loop. The distance between here and here is governed by this whole pathway around it. So you want the machine to be stiff, and you need to set that zero very accurately. If you set the zero too high, you don't actually cut the traces properly. If you set it too low, you're removing too much material. At a minimum, you're wasting time. And if you set it too low, you can break the little end mill. So one way to zero it is just by mounting it. And this is what I do. So here's my board ready to machine. I've got nice clamps holding it down. I loosen the tool in the collet, bring the collet most of the way down, And then by hand, I lower the tool and I tighten the collet. So I've done it by just putting it in place. For that technique, the tip is when you tighten the collet, because it's threaded, it's actually going to pull your tool up just a little bit. So if you tighten it, what I then do is in the machine software, in software, I lower the Z by a few tenths of a millimeter to adjust because it moves up a little bit when I tighten it. So that's one way. Um, this is a technique where if you move a piece of paper back and forth and you lower the tool, when the paper binds, you know it's where it is, and then you adjust the zero by the thickness of the paper. And then most of these machines let you automate it. So I'm showing here's a probe. I've got it connected, and I've got my tool connected to the other side, and the machine itself can come down and touch off. So that automates the zero, but unless you know what you're doing, I don't recommend this because unless you have a good circuit, it never detects it and it plows into it and breaks the end mill. So this only works if you have a reliable circuit. And as a beginner, that can go wrong. I only do this if you have practice with it and you trust it. Even though I have all of that, the technique I usually use is I just lower it, set the zero, and then move the zero down in software by a few tenths of a millimeter. Depending on your machine, there's either a set screw or a collet that holds the tool. An important tip, Ricardo is noting, don't forget to disconnect the clamp, otherwise you start up the machine with it connected. The set screw or collet is snug. You don't use all of your strength. If you push as hard as you can strip these threads. And it's just bad for the budget of your lab. You have to replace them. So these are snug, but you don't need to use all of your strength. Now, if we go back to this picture, when the tool you're using is brand new, it's so sharp, you get very fine shavings. Then the tool gets a little bit rounded and it machines happily. Then towards the end of its life, starts to get dull. So instead of cutting cleanly, it starts to smush and you get a rough finish. That's how you tell when it's time to replace the tool. But in any of those scenarios, after machining, there's shavings. There might be a little bit that's non-uniform. So after you machine, you deburr. And so one of the ways you can deburr is with a light abrasive. What I generally use is, this is just a steel rule that has a very sharp, straight edge. And I use this, I drag this over the board to deburr. And you'll be surprised. You can have what looks like a pretty bad board with a tool that's been used too long. But once you deburr, it can look quite good. So after that, then you wash the board. Washing is to get rid of all of the dust from machining, the fine shavings, but it's also to get rid of the oils from your finger. Your finger oils over time will tarnish the board. So before you solder the board, you just wash it in soap and water. Then, so far we're talking about one-sided boards. But if you make two-sided boards, you're going to flip it over. And there's a number of techniques for that. But this is a nice technique that I first saw from Kerala, which is if you make a board like this with this little tab, when you flip it over, the board exactly fits in the slot left behind. And so it aligns the top and the bottom. Okay, so that's machining. Machining is a workhorse process. it takes a relatively inexpensive machine, completely predictable, produces really nice results, and you can get down to reasonable resolution. There's a few other processes we use. So the vinyl cutter is the least appreciated. Oh, let's see. Yeah, I didn't mention climb versus conventional. So remember from the machining class, the tool is like this. This is called climb machining. That's conventional. Conventional is good for forces because the tool's pulling in. Climb is bad for heavy machining because the tool's pushing away from your work. But generally, we do climb machining for this because climb machining makes a cleaner cut and leaves a cleaner finish. So the vinyl cutter, so this is an example of the vinyl cutter where, see, he made a circuitry, he made a 3D, yeah. So here he's making a circuit that's not flat, that's actually wrapped around a cube. And he has really good documentation on, here he's making a flex circuit. And so the machining process needs really no skill and is completely predictable. The vinyl cutter process needs practice. So here's the sequence. He's going to start with the copper. Then the copper is on a backing intentionally that it doesn't adhere to. So if you try to vinyl cut it, it'll smush around. So he's going to take the copper, he's going to put it on an epoxy film, and I'll talk about the materials, and then he's going to put that on a backing sheet. He's going to vinyl cut that, and that's all keeping the copper in place. Then comes the weeding. So let's see, in a minute you'll see that. So if you cut with too little depth or force, you don't cut through cleanly. If you cut with too much, you shred it. But if you get it just right, then you can do what now you're going to see here. So let's say, oh, I guess he's going to cut another one and then weed. So when it's time to weed, there's a couple tricks. So the first trick is you don't lift up. That's trying to pull everything up. You shear. What you want to do is you want to shear in plane rather than lifting vertically. That helps to hold down. When you get all of that right, it's kind of magical. You just start pulling, and magically the traces are left behind. You just start pulling, and if everything's going well, he's nicely shearing in plane. He's got some tweezers to help hold things down, and you just start pulling, and it leaves behind your traces. And the machining process takes about 10 minutes a square inch. The vinyl cutting process, it's just the length of the cut, and it might take a minute to do all the vinyl cutting. The time goes in the weeding. Now, what's then great about the vinyl cutting is you can make as many layers as you want, and you can lay up a multi-layer circuit board with it. And so, let's see, this was a student who used the vinyl cutting he took the cardboard assignment and then he vinyl cut traces and used it to make circuits on top of the laser cutting. This was a student who really fell in love with the vinyl cutter, and she did most of her work vinyl cutting. So on the right is a milled board, on the left is vinyl cut. And one of the things she's doing that's a really good tip is when you vinyl cut, the traces aren't adhered as strongly. And so like a connector could easily pull out. And so if you look here, you can see just a little curvature. What she did is she epoxy encapsulated it. After she made everything, she just mixed epoxy and spread the epoxy, and the encapsulation keeps all the traces down. And so many people try the vinyl cutter and say it didn't work. It does work, but you have to get in the right range of parameters, not too deep, not too shallow, good weeding. There's some skill to it, but in return, you can make boards of any size and shape. They can be transparent, they can be flexible. And so there's a subset of people who fall in love with the vinyl cutter. And you could do, all of the circuits in the class with that. And you can mix them. This was a student who wanted to make a funny shaped board. And so she started with the vinyl cutter copper, but then she applied the vinyl, but then she machined it to do a hybrid between those. So that's the vinyl cutter. And then comes the lasers. So the laser engraving PCBs is rapidly displacing machining them for some purposes. So this is using, so going back to the laser cutter week, the CO2 lasers that are 10 micron laser light doesn't do anything to metal. And in fact, it's very bad to reflect it back in. 1 micron laser light that's still shorter infrared, but shorter wavelength that comes from fiber lasers does a very good job of removing copper. There's a little detail you can get fine hair that you have to remove by defocusing or cross-hatching. But then this works beautifully. Just the laser, let's see, that's just a Trotec ad. I think there's a video on this page of just the laser runs back and forth. Instead of everything I just described about the milling, you use the laser to remove the copper. That's with a fairly expensive fiber laser, but they've come way down now in the X-tool size fiber lasers. So this is a nice page on using the laser to make the PCB. And then they're also doing a second layer, which is a solder mask. And I'll talk some more about that. This page talks about a process that I do, which is the fiber laser does a great job of removing the copper, but it struggles to cut out the board. The milling machine does a great job of cutting out the board, but can't work as high resolution. And so they work together very nicely, where you can either laser engrave and then mill, or the lasers have cameras. Let's see, what is this link? Oh, okay, on the Trotec, yeah. So what's happening here, and this is what I do, is if I have a low resolution board, I mill the traces and the outline. But if I have a board with tiny features, I mill the outline. Then I go to the laser, and I use the lasers have a camera typically, and I use the laser to position my job, and then I use the laser to make the fine features. And then most recently, what's come out are UV lasers used to be very expensive. I had one in my lab that it was a $100,000 machine. But now, for example, from X-Tool, you can get a $4,000 UV laser. The UV laser light is now 300 nanometers, very short wavelength. And that does a really great job of removing the copper very cleanly. And so these have just emerged, but the UV lasers are emerging as the preferred tool of choice. The 1 micron lasers can lead to burning of the substrate. The UV lasers just very cleanly remove the copper. And then this last link is a paper from my lab that was looking at a really interesting process called LIG, which is laser-induced graphene, where you can use the laser to take an insulating material, The laser turns it into graphene, and graphene is a conductor, but not a great conductor. So you can use that for if you just need, for example, a sensor interface. But you can then easily plate the graphene. So you use the graphene, you write LIG, and then you plate that, and then you make flex traces at very high resolution. So here's a paper on that process. So the milling machines work great. The lasers, if you have them, let you make finer features, which I'll talk about. Then you can print circuits. This was an example of using a conducting ink to make a printed circuit. You can electroplate. This is just a link to electroplating. And then at low resolution, this was years ago, my students helped start sewn circuitry, where you sew conducting threads to make fabric circuits. So I recommend everybody start with milling as a basic technique. Play with your vinyl cutter to see how you use that, and if you have a laser, learn to use that. Okay. Next is materials. Printed circuit boards that you look like this, typically greenish. That's FR4. It's glass fiber in an epoxy matrix. This is hazardous to machine because it makes little fibers. If you breathe them or they get in your skin, this is the same hazard as asbestos. So we don't use these in the labs. What's good about them is these are good to higher temperatures, but it's hazardous for machining. We use what's called FR1. And so this is copper with a phenolic material. It's a resin and a material like paper. And there's no hazard. Oh, and the other issue with FR4, in addition to being hazardous to you, it'll rapidly kill your tools because you can't machine glass. Now, for FR4 and the lasers, there's the foreground reason we don't use FR4 with the lasers is it's still hazardous to cut out your board outline. But the other one is the resins used with FR4 can be hazardous when the laser cuts them. And so they need ventilation like any sort of, like fume hood type hazardous ventilation. So for those are the reasons why we stay away with FR4 with the lasers. Lasers can remove the traces, but they can make hazardous fumes, and you still have the issue of cutting the FR4 that we don't like to do. Finally, you can get garolite is the machinable substrate. You can just buy boards of garolite, and you can make your own PCB stock with that. Now, for flex circuits, commercially, it's done with Kapton typically. Pyrolex is a thermoset adhesive. To do it in the fab labs, we use this material that looks a bit like vinyl for the vinyl cutter, but it's a cast epoxy film that works at much higher temperatures. Yes, Kieran, FR1 is completely safe. It machines easily. There's no hazard to the dust from it. And then we use a copper tape. And so this is in the fab lab how we lay up flex circuits. There's a funny units. The copper, when you buy the boards, is spec'd by the weight per area, but common is 1 ounce, and 1 ounce copper is only 35 microns thick. So that's why our depth of cut is so shallow. You only need to go, less than a millimeter even, but a millimeter is plenty to remove it. Anything more, you're machining deeper than you need to. That's how thin the copper layer is. Okay, so then comes, here's a board I designed, and then here's the board now made not in the lab, but from a board house. So thanks to our friends in Shenzhen, Two of the most common ones are JLC PCB and PCB Way. They've brought the cost way, way, way down. So now, and also they've brought the order size way, way, way down. So now for $5 or $10, you can order a little batch of boards. Depending on where you live, the main cost is just shipping. So, but it might be $5 for a little order and $25 shipping. So for $30, you can order boards from them. Now, note that doesn't eliminate the chemical waste. They're generating the chemical waste, and you have to trust that they're just getting rid of that safely. But it takes about a week turn time to send a board to them and get it back. Garolite is safe, easy to machine. FR4 is like fiberglass, to the chat. So 1 to 10 boards I would do in-house. When I want more than 10 boards, I would send that out, or if I have features that I can't do in-house. So going back to this, the key design rules are how skinny can a trace be and how close can a trace be together. Down on the page, I've got a link to this file. And here I'm varying the line width and the trace spacing. And then I show making this with many different tools. And so here I'm using the 1/64 inch tool. And so it can't get in that space, but it's getting down to below about 10,000ths of an inch. Here's the same thing done with a V-bit. Here I do it with a fiber laser. Here this was with the galvo laser. And you'll see the laser can make a much smaller spacing than the end mill. So when you design your board, you need to design around the design rules of your board house. In-house, it's maybe 10 or 15 mil, where a mil is 1,000th of an inch. The board house is typical is 5 mils. You can go below that, but it costs much more. Now, a key design question is layers. So here's a one-sided board. It's all on one side. That's easy to make. This is, I'm calling it a 1.5D board. You'll see a 0 there. That's for, I laid out this board, but I have to get a trace from over here to there, and I had to cross here. And so the easiest way to do that is just, this is a 0 ohm resistor. It's a component like a resistor, but it's a perfect conductor. And so if you just have a few crossing points, you don't need a 2-layer board. You can just use a 0 ohm resistor to hop over. Then this is a 2-layer board. So I'm using what's called a via, and I've got some traces on the bottom side, and the via stitches between the top and the bottom side. And I'll talk about in a little bit how we make the vias. Then this is an example where I mill a board, and then I'm making a few layers, and I'm using the vinyl cutter to make layers on top of it. Common in board houses is 4 layers, where you have top and bottom traces, and in between you have a power plane and a ground plane. And your PC or your cell phone might have a 10-layer board. So when you send a job to a board house, in addition to the traces, there's a mechanical layer that's the outline. There's a drill layer that are the holes if you have vias. There's the solder mask, and what that does is it prevents the solder from going anywhere but the pads. It makes it easier to solder. And then there's a silk screen, which puts text on the board. And so those are all jobs that you typically won't do in-house, but you send out to the board house. And then vias, when you route, depending on your complexity, you may find you need to go down, over, and up, so you need to go on 2 layers. So if you just here's an example of a board where this was too far for a 0 ohm resistor, but I only had one problem place. I just had to get from here to there. So there, rather than a two-sided board, I just use a wire jumper. So if you just have a few of these, you can use a wire to make that crossover. Um, these are header pins we use for components, but you can use the header pins to make vias. So you have a trace on the bottom, a trace on the top. You put the header pin through, and you use that to solder through. This is a nice technique. These are little rivets that are designed for this. And what you do is you put the rivet in the hole and you tap it down. And you use the rivet to make the via between the top and the bottom. In a commercial board like this, these are plated. So they drill it, and then they do what's called electroplating in a chemical bath to make the via. And then when you do more complex boards, when you have more than 2 layers, a blind via is one that stops on an internal layer, and a buried via is one internally between layers. Yeah, Sahin is noting the rivets can cause problems. Sahin, I never use the rivets by themselves. I always, once the rivet is in, I flow a little bit of solder to make sure it's anchored well. So blind and buried vias are much more complex to make. So of these, start with 0 ohm resistors. If you need to go a longer distance, 1 or 2 wires. If you have still more vias, you can use the headers. If you have still more rivets, and then eventually when it gets too complex, when I have lots and lots of vias, then I send it out. Although right now we're experimenting with using the lasers and copper on Kapton to make multi-layer boards in-house. That's a process we're experimenting with. Okay, so let's go back to our search engine. Octopart for components. So if we take this chip, you can get it in the dip that we no longer use. This is a surface mount. And then this is a QFN package. This one you can solder by hand because the leads stick out. This one you can't solder by hand because the leads are underneath and you need to do reflow. And I'm going to talk about that. So the only through-hole components we use are ones where you need it for mechanical anchoring. Otherwise, all the other uses are surface mount, and then the tiniest are what are called chip scale. So now we get to Neil hates breadboards. Breadboards are popular, but the reason Neil hates breadboards are for a few issues. One is breadboard needs through-hole components. So you need a whole separate, but we don't use the through-hole components on PCBs. So you need a whole separate inventory. You need a complete separate inventory of through-hole components. Second issue is electrically, they're not great. There's a lot of parasitics. A third issue is when you make something with the breadboard, there's no documentation. And if you come back a week later, you don't even know what it is. And then the fourth issue is if you take up your breadboard and walk around, the wires can start to walk out of the little fingers and it can stop working and you don't know why. So the process we're going to cover in an hour, you can go from a design to a board, and you can do lots of iterating and modifying the design. So you can edit PCBs, but it forces you to document, and it's a reliable process and it's a scalable process. Parasitic is resistance and capacitance that's not in your circuit, but just comes from the breadboard. So that's why we're not passing through breadboards and we're going right to PCB fabrication. So the heart of this week, is, let's see, DigiKey periodically updates their site. What this is a link to is DigiKey has thousands of kinds of solder. So to solder, you can use a soldering iron like this. Better is a solder station like this. This has the soldering iron, it lets you control the temperature, but it also has this side, which lets you do hot air. And the hot air is going to be essential for reflow. A fume extractor helps to take the fumes away. And then I strongly recommend a microscope like this, really helps the soldering. And just a final note is almost anybody who's done a fair amount of soldering at some point has been looking one way, reaches the other way, and grabs the hot end of the soldering iron. That's a bad idea. Don't do it. It's not terminal, but you get a burn, and you should just be aware of that. ROHS is the European standard to eliminate heavy metals. And so solder used to be based on lead, but now because of ROHS, most commercial products use lead-free solders. If you see leaded solder in your lab, complain about it. Your lab should be using lead-free solder. So here's a matrix of, this is a leaded solder joint, this is lead-free, and there's also special low-temp solder, and all of them make nice joints. And then what I'm showing here is paste. So wire solder, you heat and solder. Paste is a solder paste. You dispense the paste, you put your components in it, and you reheat it. For components with leads you can see, you can use either. But for the components where the leads are underneath, then you need the paste. So soldering is surprisingly subtle. So if we start with the wire solder, if you have a chip, here's a lead coming down, here's the circuit board. Something you'll get tired of hearing me say is shiny and smooth. If you look at my joints, you'll see they're shiny and they're smooth. The opposite of shiny and smooth is what's called a cold solder joint that are lumpy and grainy. It's surprisingly subtle and can drive you crazy. Somebody who's good at soldering will come in and in 15 seconds do that and have a perfect joint. And as a beginner, you can spend hours failing to reproduce it. So what's going on is first comes the soldering iron. Your soldering iron tip needs to be clean and needs to have a thin layer of solder on it. That's called tinning it. If your iron is gunky, it doesn't do good heat transfer. Then the iron comes at the joint. If you heat one side or the other, it's not uniform. Then when I'm soldering, I'll take the wire solder and I'll add a little bit more solder. And what that does is it makes a little ball of solder here. What that's doing is it improves the heat transfer, so the heat flows better. Then the key thing at this point is to wait a little bit. I'm waiting for the heat to flow up the joint and out the board. I'm gently probing. And when the leads get hot enough, the solder will flow up and flow out. And then now the key thing is, then I have to wait just a little longer. If I take the iron away, it's not done. So I wait for the solder to finish flowing, then I take the iron away. All of that takes about 15 seconds. But if you skip any one of those steps, you're forcing the solder, it's not hot, and you get a lumpy joint. And cold solder joints are really nasty because they might or might not work, and it can vary. They're sort of grainy and imperfect. They can be really hard to debug. And so if I ever see one, the first thing I do is reflow it. I heat the joint and reflow it again. So that's manual soldering. Then with the paste, there are a number of ways you can do it, but this is a link to doing it with a stencil. So here what we do is, this was an instructor boot camp. You machine a stencil. You use the stencil to spread the paste. Here's the paste on the pads. You stick down your components, and then you use hot air to reheat it and solder it. And so now, on a hot plate, you heat from below. That works with FR4. That doesn't work with FR1. FR1 is not a good thermal conductor. So for FR1, you have to heat from above. So a solder station like this has a hot air gun that it's like a hot air dryer, but it lets you control the airflow and the temperature precisely. And you heat from above rather than below to reflow it. So there's a number of variants of how you do it. So when we get to input and output devices, we'll be using components that have very tiny leads. So what I'm showing here is what's called heat and squish. So here, solder was put on the pads. Too much was put. It wasn't carefully placed. You heat it, and when it gets hot, you just poke the component down, and it squirts out the unneeded solder. And then you come in and you remove the excess solder. Another technique is tin and heat. Here, what I did is I put solder just on the trace. I put too much solder. I remove the excess solder, leaving solder on the traces. And then I heat and I poke my component down. And then finally, the most straightforward one, both of those don't need a stencil. The most straightforward one is you actually use the stencil, like I showed you before, and spread the paste with it. And the lasers I described, the fiber or the UV lasers, also make great stencils for dispensing paste. And so once you get used to it, yeah, okay, that's right. So here what I'm showing is you can put solder on pads and use hot air to poke the component down. And then here's an example of the whole hot air sequence. So here I dispensed the paste. This is a somewhat larger part, so I don't need a fancy technique. And you'll see I actually made a continuous bead. I poked my component down. The paste wants to go where it's hot. Now I'm heating the component with the hot air, and it's kind of magical when you watch it. First it looks runny, then it looks a little bit dried, and if everything's going right, magically it just suddenly turns to silver. The little solder grains connect, and the paste turns to silver, and everything is tacked down. So you need to learn to do reflow for the smallest components, but some people, once they discover paste, never go back to wire solder. Instead of the sequence I just described of this sort of dance of heating and flowing and soldering, you can ignore all of that if you just take the syringe and dispense the paste, poke your components down, and then just reheat the whole thing. So stuffing is the term of art for attaching your components. First, note the orientation. Integrated circuits, diodes, have a right way and a wrong way to put them down. And every instructor on this call has gotten that wrong at some point. You need to make sure you get it down right. One of the trickiest things is, let's see, let me find, okay, yeah, this was an image, I didn't show this. Yeah, so let's go through. Here, uh, Marius, you can use the iron with paste. That that's fine. I generally don't, but it's not sacrilege. It just seems extra work. So let me go through the sequence. So what I'm doing here is, if you don't get this right, the component's running away from you. So I'm going to take my iron. I'm going to make a little bump of solder. Then here what I'm doing is I'm tacking down the component. I'm using the solder to attach, heating the solder. I poke my component in place, and the solder is holding it in place. Okay. Now I'm going to flow the solder on a joint, go to the next joint, and I'm going, one joint at a time, making my way around. I get back to the first joint, and the very first joint isn't a really good solder joint, so I reflow it and then use it to attach. And so this is called tacking components down. You use a little bit of solder to hold the component in place while you do the other joints, and then you go back and finishing it. You want to stuff low to high and in to out. A common mistake is to do the big components first, and then you have to reach around them to do the little ones. So you want to do the little ones first, and then get to the big ones to stuff. If you're doing a one-sided board, if you have a two-sided board, the components go through. If you're only making a one-sided board and you're using a breakout board like this, which we'll talk about, the trick to do that is the header comes from below. I solder on the top side, then I push the breakout board on top, and then I solder on its top side, then I trim both sides. So that's how you do a one-sided header. Yeah, Garrett, for reflow, an ordinary kitchen convection toaster oven does just fine. The key thing is you need to label it to never use it for food. Desoldering is, you might desolder because you made a mistake, but here I'm desoldering because I have tiny leads and I intentionally put in too much solder and then I remove the excess. There's many ways to do it. The most useful is braid, but it's very tricky. This is solder braid. And what you do is you poke the braid against the joint with your soldering iron. The reason this is tricky is if you try it, you might conclude it doesn't work. So if we have a bad joint here, you bring in the braid, but it's like a pump you prime. You have to add solder to the braid, and then that starts the solder flowing, and then the braid pulls away the excess. Finally, a great technique is if this is the wrong chip or the wrong orientation, you grab the part you don't want with your tweezers, you aim the hot air at it, and then when everything gets hot, the board drops away, leaving you holding the bad part. And with that gravity technique, it's easy to remove components. So here's an example where I was making a board and I made a mistake. I had connected the wrong leads, and that's very easy to do. Rather than start over, what I did is underneath here, I cut the trace I didn't want, and then I made a wire jumper to go where I do want. And so by cutting traces and by using wire jumpers, you can do a lot of edits. And you'll find commercial boards shipping in products that have cut traces and wire jumpers because they made a mistake and they want to use up the bad boards before they have new ones made. For the tiniest components, there are stations that help you place it. And then when you want to make lots of boards, you use a pick and place. And these have come way down in cost. This is an open pick and place to automate the component placement. And then at the very end, you can encapsulate your board to strengthen it and protect it from the environment. Okay, two final things. To get your board to the machine it in-house, typically, if you're using mods, we use PNGs. The board houses make Gerber. And so thanks to our friends in Kerala, there's a nice Gerber, a KiCad plugin that'll produce the PNGs for you from the Gerber to go to mods. KiCad can also, let's see, let me go back. Let's see, the KiCad can produce SVGs, and you can read in the SVG and send that out. If you have one of these Carveras, it can automatically change the tools. This is a workflow Quentin did for that. And then a key thing to be aware of is the footprints of your packages. The key thing that matters is the pitch. So here's an example where I was using a part with a fairly fine pitch, and I used the wrong footprint. So when I made it, these were all shorted. But I could still make this just by thinning the pad. So I went back and I thinned the pad and the footprint, and now there's enough room for my end mill to get in to make it. So you need to be, if you design your board and it doesn't fit, you need to check not simply the spacing between the pads, but the pitch of the pads. And so now let me go to, here's this test part. Here's making it with a 1/64 inch end mill. Here's making it with a 10th inch end mill where it gets in smaller. Here's the V-bit, and the V-bit does a fine job with it, and then making it with the lasers. And so the first task to do this week is run this test, and it should look perfect. If it doesn't look like this, you need to check the state of your tool, the state of your stock, the state of your machine. It should come out perfect. Now, this is a link to a debugging recitation. There's a high probability that for this week, I want you to test your board, and there's a high probability that you'll make it and it won't work. So the first thing to do is inspect the joints. A solder bridge, let's see, a solder bridge is where you, let's see, let's go back to here. If here's a pad and I'm attaching a component, and I've machined around it, but I didn't leave much space. When you solder this, if you're not careful, the solder can actually short over the gap. So it's a good idea to leave extra space around your components so you don't have to do tricky soldering, but look for a solder bridge. And then look, are your joints shiny and smooth? If they're not, you can heat it and reflow it. Check the components, that you're using the right component, it's oriented the right way. Check the data sheet. Any of the instructors have designed a board and made a mistake and connected, made a mistake with the data sheet and had the wrong pin. Make sure the connectors point the right way. A good thing to do is measure the voltages in the circuit. A common symptom of a problem in the circuit is if you give it 3 or 5 volts and you measure the power supply and it's less than 3 or 5 volts, if the power supply is drooping, it's a good sign that something is shorting somewhere, fighting against the power supply. And finally, if you pass all of those tests, then take out the oscilloscope or the logic analyzer. Debugging at this stage, it might be you made the circuit wrong. It might be you designed the circuit wrong. It might be your low-level code is wrong. It might be your high-level application code is wrong. The problem could be in many different places. And these are particularly tough to debug when there's a problem in more than one place. And so that's why you should have right at your workbench an oscilloscope and logic analyzer so you can reach in and check the signals and see what's going on. So as a group, make sure you can produce beautiful PCBs. And then as a group, I want you to send a design to a board house. It's up to you can send the job without actually buying it. So just as a test, if you go to one of the board houses like JLC PCB, so there's oh, I don't know if I showed that. There's a KiCad. See, I don't have that. Oh, I had that linked in the design week. I'll link. There's a KiCad plugin that produces the file for the board houses. When you go to the board house, it's very easy to upload your board, and then they'll analyze it and give you the feedback on it and show you what they'll make. So I want you to submit a design to a board house. It's up to you if you actually ask them to make it, and you don't need to each do it separately. But I want you as a group to go through sending a job to a board house. Then each of you takes a PCB you designed with an embedded microcontroller, make it, and crucially test it. For this week's assignment, we want to see your board working. Start by machining to learn that. If you have a nice laser, you can use the laser. Don't neglect the vinyl cutter as a commonly neglected but nice process. And at the end of this week, you'll have a working PCB. Now, you need that because next week we're going to be making boards with sensors. Next week, boards with actuators. The week after that, boards that communicate. You won't be able to do those unless you have working boards this week. So it's not enough to make the PCB. To finish this week's assignment, you need a working PCB all the way through. Okay. Once you master this, you're often then designing your own circuit boards. Use the global open time, and don't neglect the subtlety of soldering. You could make practice boards and just practice soldering. It's a subtle skill to master. It looks simple and it's easy, but as a beginner, you could spend a whole day failing to get a good joint until you master the subtle, graceful art of soldering. Yes, Jeff, absolutely. For this week's assignment, your board has to have a microcontroller, and that's because we're then going to cover interfacing microcontrollers. Yeah, no to the 555. Ignore Hank. A microcontroller in the same package of the 555 that's costs less than the 555 does more than the 555, including what the 555 does. I used to love 555s. Anyway, but Jeff, absolutely. At the heart of the electronics part of this class is learning to design around microcontrollers. And so for everything coming, you need circuit boards with microcontrollers. So if we go back to the microcontroller week, if in doubt, an AVR 412 we love. The Xiaos are great. You could use the SAMD family. Any of the processors we covered. This can't be, so the processor goes into your board. You're not making a peripheral for somebody else's board. You have to design a board around a processor, and it can be any of the ones we covered. Okay. Use Saturday, open time, great support, no recitation this week, and I'll be interested to see what your boards can do next week. Happy PCB fabricating. Bye-bye.
Bye.
Goodbye.
Bye.
Adios.
Bye.
Bye. Ciao.
Bye-bye.
Hasta luego.
Ciao.
Bye.